All right, so welcome to Chapter 2, Section 3, and this is where I'm going to need you to, how do I say, wake up, grab some coffee, an energy drink, and settle in, right? Because our journey really, truly begins in Section 2.3. And let me go ahead and give it a title, and we'll start to unpack it. Ready? So we're going to be discussing differential equations, right? But we're going to discuss first order linear differential equations. All right, so let's break that title down. So we got linear first order differential equations. Now, so let's start with the first order part. Obviously, a first order just means that the highest derivative we are going to be dealing with in this section is the first derivative, right? Just y prime, f prime, dy dx. So that's what of the first order. Now let's kind of discuss why is it that we consider it linear. So let's back up. Let's back up to what we know about, in general, what we know about linear equations, right? So we know that what determines that an equation is linear is the power of the exponents over the variables x and y. So in this case, we have a is just some arbitrary real number, and b is some arbitrary real number. We'll assume that a and b are not zero. But what we have is, as long as, obviously, you know this already, but as long as we are dealing with powers of 1, then we know that the graph of such an equation is, what the heck just happened? The graph of such an equation is linear, okay? All right, so now let's see if we can try to shift from here to a linear differential equation. So you can probably see, I'm going to erase these exponents here, just because I want to just make sure that you don't think they're prime symbols. So, but the idea is we have a function of x attached to dy dx plus a function of x attached to y, and that is equal to a function of x, okay? So we know that this is linear because we have you can think about the power of the first derivative being 1. We know that we are also going to assume that these a of x, a sub 0 of x, and b of x are continuous, and they are differentiable functions of x. Now, what's important, and this is where I'm going to kind of slow down for just a second. So actually, I'll tell you what. What I'm going to do is, let me kind of give a disclaimer. At that point, what I want to do is proceed from here to a more simplified standard form of these types of equations. Then I want to show you why the methods of separation will not work, okay? So first, the disclaimer. So I need to be able to unpack this technique for you, and that's going to take me some time in this first video of this section. And I'm telling you, this is not some proof that you can skip over to get to the formula and then use the formula to do the problems, because you can't do differential equations like you are baking, following a recipe to bake some cakes. It's not going to work. And I'm telling you from teaching this for a long time. Every single problem from now till the end of this class every problem, the title will say, solve the following differential equation. If you don't truly understand the roots beneath these techniques, then you are not going to know which technique to use, right? It's going to say solve the following differential equation. Do I use method of separation? Do I use this method of linear? Do I use the other, 10, 12 techniques that we're going to learn in this class? How will you know which method to use? Unless you can start to get a feel for, again, what's happening beneath these techniques. So that's the disclaimer. What I want to do right now is I'm going to simplify this linear differential equation, and all we're gonna do is we're gonna move some stuff around. Okay. So for example, I just want to show you where this comes from. I'm just going to divide. I'm going to divide by, I don't know what that is. I'm going to divide by a sub 1 of x. A sub 1 of x. I'm going to divide both sides of this equation by a sub 1 of x. Okay? So when I do that, what I have now is dy dx plus, and now what I'm going to do is, let me not jump too many steps. So I'm going to take this a sub 0 of x over a sub 1 of x, which we're going to think of this as some coefficient that is attached to y. And what I'm going to do in just a second is I'm just going to give this another name, right? So it's not so messy. I'm going to call this p of x in just a second. But let me go ahead and finish this out. So, and that's equal to b of x divided by a sub 1 of x. All right, so first step is just divide by that a sub 1 of x. And what I'm going to do right now is I'm going to rename this quotient, and I'm going to rename this quotient. All right, so henceforward, a sub 0 of x divided by a sub 1 of x. We're just going to call that p of x. Make things nice and simple. And then henceforward, b of x divided by a sub 1 of x. Henceforward, we're going to call that q of x. So, all right, let's, I used q of x. I want to make sure I'm using the same, that I'm not quite sure if your textbooks used p and q or if they used something different, but okay. So nevertheless, so we're good to go at this point. So let me rewrite this equation. But now let's go ahead and use p of x and q of x. Ready? So now dy dx plus p of x times y is equal to q of x. Okay, so this is what we refer to as the standard form. Okay, so, and what is the goal? So let's go ahead and state the goal. So the goal is to be able to solve these types of differential equations. And what does it even look like to solve? Well, take a look at that derivative, dy dx, right? So there is some y out there that you took the derivative of to get to this function, right? And so to solve, in other words, to solve this differential equation is simply to find that y function that you took the derivative of, okay? It's not, we don't want to think of it as so we're just, it's differential equations that we're just going to redo integrating. You know, that's not quite the way you want to think about this, and I'll try to explain why in just a second. So let's kind of move over to this next page here. Let me figure out what the heck I just did first off. Let's go ahead and rewrite dy dx plus p of x y is equal to g of x. Okay, so this is a linear differential equation, and what I want you to understand is this is not a separable equation, right? Remember last section we learned about that method of separation to solve these differential equations. That won't work here. You can't use the method of separation. I mean, think about if you were to try it. Remember the separation method. We wanted to get dy on one side of the equation and dx on the other side, and we wanted all functions of all x values to be on the right side and all y values to be on the left side, and then at that point is when we integrated both sides, right? So what if you tried to do this, right? What if you tried to get y dy on this side and x dx's on this side? Well, let's see what would happen. Well, this is not going to work, so you could, if you don't believe me, well, why don't you try, maybe we try distributing dx, right? That's one way to get dx to the other side of the equation. So that would leave us with dy plus, what we got, p of x y. We'd have to distribute dx there as well, and that's equal to g of x dx. So if you first try distributing, all right, well, we could take this entire term and bring it to the other side of the equation. See what that looks like. So that would give us dy is equal to g of x dx minus p of x y d of x. Now maybe you're thinking, oh, well, I could just factor out a dx. That would get me to where I want to be, but let's try it. So we factor out a dx. You're left with g of x minus p of x y. So look, you have your dy on the left side, you have your dx on the right side, but you see this problem, right? You want that y, you would want that y variable to be on this side of the equation, and you're not going to be able to do it because, right, I mean, you have to distribute a dx to this term. There's just no way. The method of separation does not work. So separation of variables does not work. So then how do we solve these linear differential equations? Well, so here's what I'm going to do, if you'll allow me to. I'm gonna revisit the product rule, that you would have learned back in Calc 1. Just you'll see why. You'll see why I'm doing this in just a second. And then what I'm going to do is I'm going to introduce this magical function that does all the heavy lifting for us, right? So I'm going to introduce this magical function, and at first we'll just leave it as magic, and then later I'll come back and I'll explain what is really happening in order to make this work. Okay? So really quickly, so the product rule. Remember, if let's say you had a function of x times another function of x, and you wanted to take the derivative of it, right? I mean, that, in other words, like let's say you had x squared times sine of x. Well, you could take the derivative of that, but it would require the product rule, right? And so we'll just, using the FG notation that we used back in Calc 1, we'll just say that U of x is f of x, and we'll say that p of x is the g of x. So what would that look like? Well, let's, again, there's a reason why I'm revisiting the product rule, so let's go ahead and finish it out. So we'll just let, in our case, f is going to be u of x, p, my apologies, so g is going to be, look at me, so g is going to be p of x my sincere apologies. Do you notice that over here I used q of x and over here I used g of x? This is just my training, right? My apologies. I didn't change anything. Q, or how I called it G here, they mean the same thing. My training in differential equations, we always used G of x here, not Q of x. So my apologies if I keep interchanging them. It's just from habit. Ready? So now f prime in this case would just be u prime of x, and then of course g prime would be p prime of x. All right. So in this case, we simply would have that the derivative of u of x times p of x would be as follows. It would be u of x times p prime of x plus u prime of x times p of x. And now, why am I revisiting the product rule? Well, all of this, walk down memory lane just to ask you a rhetorical question, and that is, do you agree with me that if you take the derivative, this would be the result? And now the rhetorical question. So if I started with this result, do you agree with me that I could rewrite it like this? Okay. So now we introduce this, what we call an integrating factor, u of x. Again, as of right now, we're just going to pretend that this is magic, right? This is mathemagic is happening right now. So let's start by writing the equation that we're actually trying to solve. Remember, dy dx plus p of x, y, and let me use q of x, as your book does. Okay. So we are going to assume that this u of x, right, this magical function, we're going to assume that it has the following property, right? We are going to assume that u of x, how do I put it? We're going to assume the following property. Let me actually just write it out. You're going to assume that u of x has the following property. Ready? Here's the assumption. That u of x multiplied by p of x is equal to u prime of x. Okay, so here's the assumption that we make right now. And I will demonstrate why this is this assumption is needed, and it is not a stretch to assume. So let's go ahead and make sure we understand that. So what is it that we assume about u of x? We assume that the derivative of u is equal to itself multiplied by p of x. Okay, so this is where we start. All right, now if we have this assumption, how does this assumption help us solve this differential equation? Okay, so let's go ahead and multiply. I'll kind of give you some steps here. We're simply going to multiply by u of x, first step. So let me grab this, bring it down, and let's go ahead and multiply by u of x. So what would that look like? So, all right, so that's just going to be u of x dy dx plus u of x p of x y. And let me actually make all this a little smaller so I have more room. Equals u of x times q of x. All right, so far, so good. So we took our standard form of our linear differential equation, we distribute a u of x, and now we are, my apologies, I have to write this a little bit smaller. It's bugging me. So let's see if I can write this a little smaller. Okay. That gets us to here. Okay, and so take a look at this part right here. We have u of x times p of x times y, right? We started off with p of x times y, but we distributed a u of x, and now we have u of x times p of x times y. Take a look up here at our assumption. Our assumption is that whenever we see a u of x times p of x, we can rewrite that as just u prime. So what's going to happen right now is I'm going to substitute. I'm going to substitute u prime in here for u of x, p of x. Okay, let's rewrite that. So now we have u of x dy dx plus u prime of x y is equal to u of x times q of x. All right, stop. Take a look at this. What does that look like? U times, okay, well, dy dx plus u prime times y. Well, I tell you what, if this is messing you up, what if I just wrote it like this? U times y prime plus u prime times y. Now, what does that look like? Say it. Don't you be scared. Just say it out loud, randomly, in public, no matter what. Just say it. It's the product rule, literally, right? Look at that. This is literally the product rule. And what we said is, look, if we have a scenario like this, then of course we can go rewrite it as d of dx, right? So the entire left side of this equation is simply the derivative with respect to x of what? So we're going to rewrite left side of equation. And that is simply, if you took the derivative with respect to x of u of x and y. So if you took the derivative, look, you could try it. You took the derivative of u and y, you would be right back to here. So we just rewrote the left side of the equation. But guess what? At this stage, so remember, the goal is to solve for y. So at this stage, what we're going to do is integrate both sides with respect to x. So what does that look like? Well, now I'll go ahead and write it just so you know what I'm doing here. We're going to integrate both sides with respect to x. And that's because we're trying to solve for y. Ready? So let me kind of copy and paste. Ready? So here we go. Let's integrate both sides. So we integrate the left side, we integrate the right side. Now, what's going to happen at this point is we're gonna leave this alone. But if you integrate a derivative, right? If you integrate a derivative with respect to x, you are just undoing the previous operation, right? If you multiply by 2, then you divide by 2. You have these inverse operations are just, you're going to undo the previous operator, right? So what that's going to look like now is you're just going to be left with u of x times y, and we're going to leave the rest of this alone for now. Now, because you integrated, whenever you integrate, you have plus c. We're just simply gonna have the plus c on this side of the equation. Ready? So plus c. I want to say that one more time in case you just fell asleep. If I integrated this side, I should have had a plus c on this side. Now, it's true, I could subtract c from both sides and have minus c, but I have no idea what c is. So it doesn't matter if I write plus c or minus c, because I don't even know what c is. So if c is a negative number, then I'm minusing c. If c is a positive number, then it's just plus c. So I have no idea what c is. So this is where this leaves us, and we're almost done. The last step, remember I started with the goal. The goal was to solve for y. So this last step is just simply solve for y. And that's easy. You just divide this side by u of x, divide this side by u of x. Okay? So let me go ahead and write that result. So y, and remember that's y of x, is equal to the integral of u of x times q of x dx plus c over u of x. Okay. So this is a linear differential equation that we want to solve. We cannot use the method of separation. We saw how that wouldn't work. But this magical function, u of x, that we haven't discussed yet, that has this property, you see how that just this u of x can get us to where we want to be, which is the solution, and that is a general solution, right, to this differential equation. It is a general solution because you still have plus c. Okay, now what's up with this magical function u of x? So here's how I'm gonna try to explain this, and I know you're getting tired. I know you want to jump to the examples, but that's the wrong strategy. So please listen to me. And if you got to pause the video and take a break, no problem, but stay with me. Don't jump to an example yet. Listen. So let's go back to that assumption u of x times p of x is equal to u prime of x, right? U is, the derivative of u is actually equal to u multiplied by p, okay? That's the assumption. All right, what we're gonna do is we're gonna solve for p of x. Right, so that's easy. Solve for p of x. All we have to do is just divide both sides by, let me kind of move this over here. So we're going to solve for p of x. That's no problem. Let's just divide this side by u of x, divide this side by u of x. All right, now I need you to go into your, let's go back in time. I need you to go back to Calc 2 and tell me what you can remember about u prime over u. All right, do you remember that? Remember u prime over u. That was the derivative of what? Do you remember? Well, u prime, so u prime of x over u of x. What we remembered in Calc 2 or Calc 1, depending on, where, I can't remember which section it is. But you should remember that that's just the derivative of ln of u, right? The derivative of ln u was just u prime over u. So what does that mean? So that means p of x is equal to, let's go ahead and state that. So that means that p of x is equal to u prime over u, which is just the derivative of ln of u. Okay. So now let's see if we can figure out where that's going to take us. So let me go back a slide, and let's grab this differential equation and park it right here so we can see how this is going to work. All right, so what that means is let's go ahead and rewrite, starting with that assumption, right? So starting with this assumption up here, that u times p is equal to u prime, but instead of writing it like that, let's go ahead and write p of x is equal to the derivative of ln of u. Ready? So let's go ahead and go back to that initial assumption. So we found out that the derivative of ln of u of x is equal to p of x, right? And remember, p of x is this function that's attached to y, right? So this right here can be represented as the derivative d of x, derivative of ln of u. Okay, so at this stage, we're going to integrate both sides. Okay, I'm trying to show you where this integrating factor comes from. Where does it come about? So if we integrate both sides with respect to x, okay, well, if you integrate a derivative, that's just going to be ln of u of x is equal to the integral of p of x dx. Now, just like we saw a second ago, if you integrate, you must have some constant of integration. So normally we put plus c here. But I'm going to, we've already saw that in the result has a c in here. So I'm going to use a different letter. I'm going to say plus k, right? This is just the, this is just from the integrating of the left side of the equation. All right. So let's see, where are we right now? So now we are going to, remember, the goal is, so I'm trying to show you where this u of x comes from. So what we're going to do right now is we're going to exponentiate both sides. So you can think of this as e to the power of. Okay? So we're going to exponentiate the left side. We're going to exponentiate the right side. Well, e to the ln, that leaves us with just u of x. And now, you remember me talking about this in the previous video, that I'll just go ahead and make sure, I'll write it again since it's been a little bit. If you have x to the power of 2 times x to the power of 3, we know that that's x to the power of 2 plus 3. Likewise, which is more germane to our topic, if you had x to the power of 2 plus 3, you could have written it like this. So you can think of it like we have x to the power of 2 plus 3, but we're going to rewrite this like this. So that's e to the power of the integral of p of x dx times e to the power of k. All right, and now e to the power of k we're just going to make a substitution. Okay, I need to make sure you understand. This is like c, right? Plus c. I have no idea what c is. I have no idea what k is. So if I have no idea what k is, I have no idea what e to the k is. But it's just a constant, right? I know that if k is a constant, then e to the power of k is also a constant. So if it's just a constant, I'm just going to label it k. So you can think of it like this part right here is about to be labeled or turned into just k. And there you have it. Here, how do we define u of x? Remember u of x, that magical function that solves linear first order differential equations. We started off, it was mathemagic. What is it? How do we define it? Well, here it is. It's just k times e to the integral of p of x dx. There's your definition. You could try, I'm gonna go ahead and stop here. You could try plugging this back in, right? If you really wanted to, you could take the following. Pretend like I'm going to drag and drop. Okay, you could grab this, go back to where we have u of x here, and plug that in. In fact, you should. It would be interesting to see what happens, but that's not what I need you to be able to do right now. What I need you to be able to do right now is just understand the following, and then we'll take a break. That there is a function out there, okay? We call it the integrating factor, and it's a specially chosen function that can help you solve first order differential equations. And finally, we define this special function as the following. All right, so where are we going to go now? So when we get back in the next lesson, I'm just going to jump right into an example. I don't think you can take any more theory. Maybe I'm wrong. Maybe you're having a time of your life at the edge of your seat in anticipation of what I'm going to say next. Maybe. But when I get back, we will jump right into an example, and we will solve some linear differential equations. See you then.